In this video, we continue subsection 3.2.4, which is about Gaussian elimination, and we're looking at case 2, linear systems with no solution. In example 3.2.9, we're asked to solve the following linear system using Gaussian elimination. We have here a linear system with 4 equations and 3 variables. Remember that the first step of Gaussian elimination is to write the augmented matrix of this linear system. Let's do that. The first equation gives us 1, minus 1, 1, 0. Second equation gives us 3, minus 3, 3, 0. The third equation gives us minus 1, 3, 1, 5. And the fourth equation gives us 3, 1, 7, 2. This is our augmented matrix. Now that we found this augmented matrix, we want to use elementary row operations to reduce this augmented matrix into an augmented matrix in row echelon form. Now, in order for an augmented matrix of this size to be in row echelon form, we need at least these entries in the bottom left corner to be 0. And so we have some work to do. Let's start with the first column. And we'll start with this 3. This 3 is in the second row. What row operation should we perform in order for that 3 in the second row to be replaced by 0? We could add a multiple of any other row to row 2. However, it's often easiest to pick a row that is above the row that I want to change. And so I'll do that. I'll use row 1 in this case. And I need to subtract 3 times row 1 in order to get a 0 in that position. And so in my new second row, I will have 3 minus 3 times 1. That gives me the 0 I was looking for. Minus 3 times minus 1, minus 3 plus 3, that also gives me 0. 3 minus 3 times 1 is still 0. And 0 minus 3 times 0 gives me, again, 0. So I have a row of zeros appearing. Now I could fill out the rest of this augmented matrix and then interchange row 2 and row 4 because I know that a row of zeros must be at the bottom of the augmented matrix. However, why don't I instead continue working on the first column? This minus 1 I would also like to replace with a 0. And I can do that with the row operation row 3 plus row 1. Again, I'm using row 1. So let's do that. The first entry will be minus 1 plus 1, which is 0. Next entry will be 3 plus minus 1, which is 2. Next I have 1 plus 1, that is also 2. And finally I have 5 plus 0, which is 5. And now I'll keep going. I'll look at this 3, which I also would like to replace with a 0. And so I will use the elementary row operation row 4 minus 3 row 1. So the first entry will be 3 minus 3 times 1, which is 0, which is exactly what I want. Next I have 1 minus 3 times minus 1. That's 1 plus 3, which gives me 4. Next I have 7 minus 3 times 1, 7 minus 3, that is 4. And finally I have 2 minus 3 times 0, which is 2. And the first row I will copy. 1 minus 1, 1, 0. That's my new augmented matrix. Now this augmented matrix is not yet in row echelon form. As I noted before, I have a row of zeros here in the second row. I need to banish this row of zeros to the bottom of the augmented matrix. So my next elementary row operation will be interchanging row 2 and row 4. So row 1 remains unchanged. Row 2 is now 0 for 4, 2. Row 3 remains unchanged, and row 4 is now my banished row of zeros. Now, is this augmented matrix in row echelon form? Not quite yet. I would like to have a 0 in the position of this 2. What row operation will help me there? Well, if I take row 3, and if I subtract 1/2 times row 2, I will get a 0 in that position. So row 3 is the row that's changing. 0 minus 1/2 times 0 is still 0. Next, I have 2 minus 1/2 times 4. That's 2 minus 2, which is 0, which is what I wanted. Next, I have 2 minus 1/2 times 4, which is 2 minus 2 again, and so I have another 0. And then I have 5 minus 1/2 times 2, so 5 minus 1, that gives me 4. And that was the only row that changed, so I have 1 minus 1, 1, 0, still in the first row, 0, 4, 4, 2, still in the second row, and my row of zeros at the bottom of the augmented matrix. Now this augmented matrix is in row echelon form. The row of zeros was banished to the bottom of the augmented matrix, and the leading entry on each row is to the right of the leading entry on every row above it. And so we move on to the next step of Gaussian elimination, which is to write the corresponding linear system, the new corresponding linear system. From the first row, we get x minus y plus z equals 0. From the second row, we get 4y plus 4z equals 2. From the third row, what do we get? Well, we have 0x plus 0y plus 0z equals 4. And, well, the fourth equation gives us 0x plus 0y plus 0z equals 0. So this is our new linear system. Now the last equation gives us that 0 is equal to 0. That's fine. But the third equation gives us that 0 is equal to 4. Since 0 is not equal to 4, that's inconsistent. And so what we found is that the system has no solution. This system has no solution. The entire system is therefore inconsistent. We cannot find a vector x, y, z that will satisfy all of the equations in the linear system simultaneously.